All right, another day, another topic. We're going to start in with radioactivity today. So we will just dive right in. I mentioned in the last class period how radioactive elements like curium used to be used to make glow in the dark dials. So you have your instrument panel here in your bombers. You'd want the fighters to, or the pilots to be able to see their instrument panels at night without having to have lights on everywhere. And so they put curium in paint with a fluorescent material, a phosphorescent material, and they would have dials that they could read in the night, in the dark. Well, the understanding of radioactivity doesn't date back that far. In 1857, this person whose name I will not attempt um, observed that uranium salts, which are just naturally occurring rocks, emitted something that would darken photographic emulsions, but you couldn't see the light. Now, that was something that was pretty much lost to history. I mean, when I was in college, we didn't learn about that. We learned about in 1896, some 40 years later, 39, Antoine Henri Becquerel, we used to just call him Henri Becquerel, rediscovered what Saint Victor had observed, but took it further. So the story of Henri Becquerel is something well known. He was doing some work with uranium salts, with uranium rocks, and he was taking pictures. And so one night he took his unused film, wrapped it up carefully in tinfoil, put his uranium rocks on top of that box, and went home for the night. He came back the next day, did some experiments. He developed his film and found that his pictures were all cloudy. And he was like, this film was fine yesterday. And so he messed around. He took some unexposed pictures and developed those and saw that they were cloudy. And he's like, wow, somehow I had my foil around the box, and yet something from these rocks exposed the film. And so he did more experimentation, and sure enough, he discovered that the rocks were exposing the film, which was exactly what had been discovered 39 years before. And so based on that, people started studying what's coming out of these uranium rocks. In 1898, 2 years later, Marie Curie started her PhD research studying radiation from uranium. And Marie Curie is the one who coined the term radioactivity. That is something that is active and giving off radiation. Radiation is energy that's leaving. When we talked about the mechanisms for heating, we had three methods, and one of them was radiation. That's what we learned there was about electromagnetic waves. This is going to be more than electromagnetic waves, although it does include them. Now, Marie Curie was a pretty amazing person. She discovered the elements polonium, that was named after her home country of Poland, and radium. Curium obviously is named after her. And in 1903, now this is a year, in 1903, she got her PhD and she got her Nobel Prize. Actually, I underlined the wrong Nobel Prize. She got her first Nobel Prize the same year she got her PhD. That's outstanding. And no, she shared it with Henri Becquerel and her husband, Pierre Curie. And then in 1911, she received a Nobel Prize in chemistry for the discoveries of polonium and radium. In 1899, Ernest Rutherford, and you might remember Rutherford, he was the one who the gold film experiment was done under. He published his discovery that there were two types. So radiation wasn't just a single type of thing. There were multiple types, alpha and beta emissions. And alpha emissions is what they were studying with that thin film experiment that convinced them that that the plum pudding model couldn't be correct, and brought them to the plum pudding model, or the planetary model. Wow, getting tongue-tied. Just 4 years later, in 1903, he added gamma for three types of radiation. Now, we honestly have more than three types of radiation, but that's what we usually focus on in a physics class, is alpha, beta, and gamma. So let's look at the differences in alpha and beta and gamma radiation. First, just the information that you see in this picture. If you have something that is emitting radioactive particles, so we just have this little button here and saying that's a radioactive source, and you have those particles go through a magnetic field, it will make a differentiation based on the charge. Remember, the magnetic force is equal to Q velocity cross magnetic field. So in all of these cases, the velocity is going up, the magnetic field is going to the right. So if you use your right-hand rule, V cross B is up crossed with right. And my right-hand rule says up crossed with right is going to make a force that pushes into the page. I'm putting the little things above to indicate that it's a unit vector. It doesn't have a magnitude, it's just a direction. So V cross B is into the page. But when you have these particles going through here, you find the alpha particles, they moved into the page. Well, what does that mean? That means that there was a force on them that was in the direction of V cross B, so Q must have been a positive number for the alpha particles. The betas, on the other hand, they come out. Instead of going into the page, they come out. So that means the charge must be negative for the beta particles. So alpha particles have a positive charge, beta particles have a negative charge. And finally, the gammas don't deflect at all when they go through magnetic field. So Q equals 0 for the gamma. So that's a simple experiment that tells you about the type of charge that the particles have. Now, a lot more work was done than that, obviously. And one of the things that Rutherford did was he studied the penetration of the different types of radiation. Now, this says ionizing radiation. Ionizing radiation means that it is going to cause whatever it interacts with to separate electrons from the material, to ionize it. And first of all, Rutherford discovered that higher energy beta particles were more penetrating. And he found that some materials, this is a less dense material, lithium, are not and is good at stopping it. So in lithium, you see that these travel quite a ways. In lead, a more dense material, the penetration was shorter. And finally, more dense produce less penetration. Less dense produced more penetration. In comparing the penetrating power of the 3 different types that he identified, he found that alphas were very easy to stop. In fact, a piece of paper is a very effective shield for alpha radiation. Betas were intermediate. So if you want to protect yourself from beta particles, you need to have some kind of, effective shielding, like, put yourself in an aluminum box or something. And then gamma was very hard to stop. You need lead barriers. So the alpha, beta, gamma, alpha is the least penetrating, gamma is the most penetrating. Alpha has a positive charge, beta has a negative charge, and gamma has a 0. So that's what we have so far. Now, moving forward, we'll learn more, but let's start with what we have so far. Which statement is true for beta particles? lowercase beta. They are the most penetrating of the first three types. Well, no, the most penetrating was gamma. The least penetrating, no, the least penetrating was alpha. Remember their alphabetical order. Positively charged, nope. Alphas were positively charged. Negatively charged, ding, 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 ding. Betas are negatively charged particles. Now, I do want to go one step further here than I have in my slides. In further study, it was determined that alpha particles are equal to helium 2 plus. That is 2 protons and 2 neutrons. Just to make sure we're clear on the nomenclature for an element, you have X, subscript Z, superscript A. And so in this, X is the symbol for the element. Z is equal to the atomic number, that is the number of protons. And A is the atomic mass, which is number of protons plus neutrons. So when we look at this designation for an alpha particle, it has Z, the atomic number, is 2, so it has 2 protons. H, the atomic mass, is 4, so the number of protons plus neutrons adds up to 4. Now I put 2 plus here. If it has 2 protons and it has a plus 2 charge, that means it must have 2 more protons than electrons, hence 2 protons, 0 electrons. So that's what an alpha particle is. A beta particle is equal to an electron, and a gamma particle is a photon. So alpha, beta, and gamma particles are actually all well-known things, but they weren't when they were discovered. Now, I have this slide here because, well, I've had more medical procedures than most people. So some medical uses of radioactive materials that I have undergone. Back when I was in college, a little football injury, I fractured my my spleen and damaged my kidney at the same time. And so they had to do a CT scan where they put this really horrible, they made me drink this horrible dye, radioactive dye. And then they also gave me injection. I swear it is the biggest gauge needle I have ever had in my arm. I was just bleeding freely when they took it out. They were so sure that they were going to have to rush me in surgery. They told my mom that, this was just a formality. And so she went shopping, and my bleeding had stopped by the time they did this, so they didn't have to remove any organs, and I was left there at the emergency room with nobody to take me home. Anyway, they put radioactive dyes in your bloodstream because then the radioactive dyes are giving off a radiation that will show up on their pictures, and they can see where the blood is leaking, in my case, see that the blood was, if it was coming out or not, actively coming out of my spleen. And like I said, it had stopped bleeding. They had plenty of signs it had been bleeding in the past, but it stopped bleeding when they actually took a picture, and so they didn't have to pull it out. When I had my pulmonary emboli, after I had been on blood thinner treatment for a while, they did what they call a VQ scan, a ventilation and perfusion scan. And once again, they put radioactive dye in your blood, as well as I think they had me breathing something too. And then they could see where the blood was flowing in my lungs and where it wasn't, and where air was flowing in my lungs and where it wasn't. And actually, let me tell you, it was scary because the technician who did the VQ scan, he said, "I can't let you leave until I talk to the doctor." And there's a problem when he says, "I can't let you leave until I talk to the doctor." And it turns out that a quarter of my lungs are dead. And that we know from the VQ scan, where they use a radioactive dye so they could see where there is blood and airflow. Okay, how do we detect radiation? You know radiation is dangerous, and we'll talk about the dangers of radiation in another lecture, 2 lectures from now, actually. But to measure your exposure, they just use, well, historically, they just used film. So you have, this is a typical badge. This is the kind of badge I had to wear every day when I worked at the Department of Energy lab. And in this badge, there is a variation of thickness of metal filters. And so those filters, and here you can see a different version, but you have those, they're going to block different types of radiation with different effectivenesses, efficiencies. And then inside of that badge, it has your name printed on it and information. They take it, they develop the film, because it was just regular photographic film that they would put in there. And then it would tell how much of different types of radiation you received. There are other methods that people have come up with, but that's the standard one that you wear when you're working around radiation. Another thing that you've probably seen is a Geiger counter, or more active, or more precisely a Geiger-Müller counter. And the Geiger counter, its design is pretty simple, really. You have a positively charged wire here, and then you have just a can all around it. And it's you have some kind of gas in there. I don't even know what kind of gas they put in there. But if you have radiation that comes through and it's ionizing radiation, that is, if it's going to separate electrons from atoms, then because of the positive voltage at the center and a negative voltage on the outside of that can, you will have the negative charges, the electrons, come to the little needle in the center. And then over here, you just have something that measures the current. And so if the electrons come here, then suddenly you have a negative charge, and you're going to have more positive charge then that flows up here to replace that negative charge to keep it at the same voltage. And it measures that current. And when it measures a spike of current, you know that ionizing radiation went through. And so it just counts how many spikes of current that it receives. And that's the click, click, click you hear is ionizing radiation going through. So that's a pretty straightforward, simple measurement technique. It measures any kind of ionizing radiation. So it'll measure alpha, beta, or gammas. Different efficiencies on them, by the way. Then we have scintillation detectors. Scintillation detectors, that was exactly not what I wanted. You have a scintillating material up here, something like germanium. And so when you have ionizing radiation go into the scintillating material, it gives off a flash of light. A photon comes out. And then underneath that scintillating layer, you have what we call a photomultiplier tube. And so you have a photoelectron that was produced from the scintillating material. And then you have, so this is a negative charge, right? So you make this positive compared to this. So you have a circuit out here. And it is connected to an external voltage source, where this side here is positive, that side's negative, and it goes up to here. So the resistors are all the same resistance. We call this set of resistors simply a voltage divider. It's a ladder here. And so each of these little plates is more positive than the one above. And, well, I should point out one other thing. This side here is connected to ground. So this side here is actually very negative. So when the electron comes, its attracted here and hits here. And then because these are all negative, when the electron hits here, it causes a cascade where more than one, like maybe 10 electrons comes off. I know the picture only shows it doubling because otherwise you run out of lines real quick. But you have maybe 10 times the electrons come off that hit it. But those electrons are going to be attracted to here, another 10 times, attracted to here, another 10 times, attracted to here, another 10 times. And so what happens is one photon produces one electron. And then each one of these stages multiplies by about 10. And so you end up with a factor of 10 to the n number of electrons. So you get a big pulse of electrons for a single ionizing material that hits there. So that's what a scintillation detector is. Those are things we use to detect radiation, either for safety or for experimentation. Now, something that I haven't talked about at all is what causes radioactivity. What does it mean? So you have a nucleus, and you know a nucleus contains only two types of particles, protons and neutrons. So in these pictures, the dark blue is protons, the light green is neutrons, and those are all clumped together. So that's a nucleus. But is the nucleus stable? Well, some are and some aren't. And so here's a graph that shows you have the, I cut off part of this. I believe I have the number of protons on this axis and the number of neutrons on this axis. And stability, a straight line here, that's the same number of protons and neutrons, does not follow that straight line. For small elements, they're pretty much stable when you have equal numbers of protons and neutrons. But when you get to more, it varies. It veers off to having more neutrons. And that's actually readily understandable. Now, when we talk about nuclear forces, up to this point, we've talked about two fundamental forces. We learned about gravitational force, that is always attractive between massive particles. That is, the charge is mass. And things either have a charge of zero, a photon has a charge of zero, or they have a positive charge. So everything else, protons, neutrons, electrons, they all have a positive gravitational mass, always attractive. Then we learned about the, I'm just going to put electric force here. There's electric and magnetic combined. And that could be attractive or repulsive. And its charge we called electric charge. And so some things had a positive electric charge, like protons. Some things have a negative electric charge, like electrons. And some things have no electric charge, like a neutron. So electric force simply doesn't affect a neutron because it doesn't have a charge. Well, when we get to the nucleus, we have two more forces. We have what we call the strong and the weak nuclear forces. So there's a total of 4 known forces. That's it. And the strong nuclear, I'm just going to focus on the strong nuclear force. It is always attractive. And its charge is, a baryon. Now, what's a baryon? A baryon means a heavy particle. Protons are baryons. Neutrons are baryons. So both protons and neutrons are affected by the strong nuclear force, and they're always attracted to each other. Electrons, they are not baryons, so they just don't participate in the force. Just like neutrons don't participate in electric force, and photons don't participate in gravitational force. So we have this force that's attractive that holds the nucleus together. But remember, protons are also participating in the electric force. And they're repulsive with the electric force. So in the nucleus, you have a force that's trying to push the protons away from each other because of the electric force, but you also have the attractive force that's trying to hold them together because they're baryons. So next we have to talk about the range. The gravitational force and the electric force are both 1 over r squared proportionality, and those give us long range forces. So if I double the separation between two charged particles, the force drops by a factor of 1 over 2 squared, or 1/4, but it's still significant. The strong and weak nuclear forces are short range. So short range, in fact, that they really only affect nearest neighbors. So when I look at these, if I were to talk about the electric forces, there's going to be electric force trying to push these two protons apart. But there's no attraction at all between those two protons. They're too far away. So when you start getting a bigger and bigger nucleus, you have more and more protons. The protons are trying to push away. The neutrons aren't repelling anything, and the nearest neighbor forces are trying to hold it together. As you add more particles, the repulsive forces are acting between all protons, whereas the attractive force is only nearest neighbors, and you start to get too much repulsive force, and the nucleus is not stable. So how can you make it more stable? Well, you put something in that's going to increase the attractions and decrease the repulsions, and what that is neutrons. Because neutrons are only participating in the strong force, they're only increasing the attraction, but they will separate or push further apart the protons, so the repulsive force gets smaller. So that's why you have more and more neutrons for stability as you get to more protons in the nucleus to push those protons farther apart to weaken the repulsive forces. Now, what's exactly going on in the nucleus is still not perfectly known. But it's an important story. We already had Marie Curie, a very important person in nuclear physics. Maria Geppert-Meyer is another very important person in nuclear physics. And hers is a story that is actually kind of distressing about humanity, although it tells you how we have improved. So Maria Geppert-Meyer, her husband was a scientist as well. And he was a scientist working at the University of Chicago, and they had anti-nepotism rules that said that you can't have both spouses earning an income. You don't need that much money for a family. So only her husband got paid. They gave her an office and they let her work, but they didn't give her money because, you already had enough money coming from your husband. Well, while working there at the University of Chicago, she came up with this shell model, the idea that the nucleus of an atom has energy shells, just like when we talk about the energy shells of electrons. And so, you have 2 electrons in S shell, it's a complete shell and it's more stable. She said we must have a similar thing when we talk about the nucleus. And indeed, it certainly appears that way. We have what we call magic numbers, numbers of stability, which we translate to be this must be a full shell. So for instance, magic numbers are 2. So 2 protons is stable, 2 neutrons is stable. Evens are always more stable than odds. So something with 3 protons or 3 neutrons is less stable. So she came up with this idea. Now, funny story that I was told, and I always pass on, is she came up with this idea during the height of the Cold War. That is when the US and Russia were not actively fighting each other, but they were scared that we were going to, come to blows. I grew up in this Cold War era where we were just scared of the Russians. And so when she wrote her paper about the shell model, that word shell was translated into Russian as grenade, like a military shell, instead of a shell like a seashell. And the Russian scientists were baffled for over a year because they couldn't understand this explosion model she was talking about for the nucleus. Just a funny little story. Eventually, at the very end of her career, I think she was at Santa Barbara then. She finally was given a job where she got paid. But it's just kind of sad that, because her husband was paid, she didn't get paid. Okay, so we have the shell model that says that we have energy shells in the nucleus. This here is something important, and boy, I feel bad that this picture is cut off. The picture should go up higher and down lower, because it starts up here at uranium 238. And uranium 238 undergoes an alpha decay. And then we have here two beta decays, a beta there and a beta there. And then another alpha, 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 and so on. We have a decay sequence that occurs with uranium. Remember, uranium, that was the first thing that, well, I'm going to start with Becquerel, that Becquerel was studying radioactive material. It's a naturally occurring rock. And it comes actually in two isotopes. Isotopes have the same number of protons in the nucleus. Iso is the same, and tope is the same number of protons. So uranium has 92 protons. If it's uranium, it has 92 protons. And we have uranium 238 that's shown in this sequence. That is one of the two common isotopes of uranium. The other common isotope is uranium 235. It has 3 less neutrons, the same number of protons. Now, when we get to nuclear energy, we'll see that a big difference between these is this one here works for a bomb or power plant. This one here doesn't, but it is the prevalent isotope. And I'll talk about why it's the prevalent isotope in just a little bit. But the uranium here that's shown, the 238, the prevalent isotope, it decays first to thorium, thorium 230. Well, remember, an alpha particle has 2 protons and 4 total particles. So if I have a uranium 238 and it decays to give me an alpha particle, now this alpha particle, it doesn't have any electrons, and I'm going to be left then with something that has 92. To here, you have to have the same number of protons. We're not creating or destroying protons yet. So it has 90 protons, and 238 minus 4 is 234 total things in the nucleus. 90 protons makes it thorium. And so the uranium 238 decays into thorium 234. And that thorium 234 then undergoes beta decay, which I'll have to show on the next page, goes through 2 beta decays to become uranium 234, which is highly unstable. This here is what we call the half-life. On average, 1/2 of uranium 234 will have decayed in 250,000 years. I said that's relatively unstable. Well, the half-life of uranium 238 is much, much longer. The half-life of uranium 238 is, I'm looking it up right now, but I know it's in the billions of years. Okay, I'm trying to look it up and my keyboard's not responding. So uranium 238 has a half-life of 4.5 billion years. 4.5 times 10 to the 9th years. And you'll notice the first beta decay, you can see there it's 24 days, 6.7 hours for the second beta decay. Well, compared to 4.5 billion years, that's no time. And in fact, 250,000 years compared to 4.5 billion years is no time. Now, uranium-235, the other isotope of uranium, has a half-life of, and we use the symbol tau, subscript 1/2, of 700 million years. So 7.00 times 10 to the 8 years. Whereas the half-life here was 4.5 times 10 to the 9 years. So you can see that the decay of uranium-238 is much, much slower than uranium-235, and hence we have very little uranium-235 left. It's almost all uranium-238 because the 235 decays so much faster. So in terms of isotopic abundance, 99.3% of naturally occurring uranium is uranium-238. And it's just 0.7% of naturally occurring uranium is uranium-235. Okay, but the key here is we have a sequence. And now I talked about the alpha. It's 2 protons, 2 neutrons, so it's 2,4. Now that thorium is going to undergo a beta decay. And so I'm going to have my thorium, 90 protons, 234 total things in the nucleus. We have the beta. A beta is neither a proton nor a neutron, and yet the nucleus only has protons and neutrons. Now I have a slide coming up to show this, but effectively what's going on with the beta decay is a neutron is being destroyed and being replaced by a proton and an electron. So I put a -1 here for the number of protons and a 0 for the number of protons plus neutrons. And then I can balance. So 90 -1 plus 91 gives me 90. So these numbers down here have to add up again. And on top, 234, 0, it's going to be 234. And so yeah, I don't even remember what PA stands for. But that's the product of the beta decay. And then this one here, the PA is going to undergo a further decay by beta decay to become uranium-234 and so on. And this is all going to end up as lead. All ends up as lead. I actually want to look up what PA stands for. PA element. That's protactinium. Yes, we use it all the time, protactinium. So these end up, and you can't see because once again it's cut off, but it ends up as lead. And boy, you'd think I'd remember which isotope of lead it is, but I honestly don't remember which isotope of lead it is. And since that was cut off, well, we're not going to see which isotope of lead it is. So this is decay sequence. It's something that's naturally occurring in rocks all around us. And you might have heard about people worried about radon gas. Well, radon gas occurs in this decay chain down here. It's about right here where the radon gas occurs. Everything is a solid except for the radon gas. Radon gas being a gas, it can escape from the rock. And so that's why we worry about radon gas, is because, you know, as long as you have uranium containing rock, it's going to be decaying. It's going to be producing all of these things along the way, you know, thorium, radium, radon. Oh, wait, there's radon right there. It's not down here. Radon, polonium, radon again. Anywhere down here, you're going to have radon because this is number of protons in this axis. So it produces radon gas, and that radon gas can then escape out of the rock. Here is my actual pictorial of alpha decay. The parent is what we call the starting nucleus. And so for the example we had before, the parent was uranium-238. The daughter then was thorium 9234 plus the alpha 24. Now, in terms of electrons, this should have had 92 electrons. And so if you have 92 electrons, you have 2 extra electrons. The alpha particle has no electrons. So your charge is still conserved. You don't create or destroy charge in a nuclear decay. It has to be conserved. There is a statement here that we will understand in just a few moments. Alpha decay occurs spontaneously only if the daughter and the helium nucleus, otherwise known as the alpha particles, have less total mass than the parent. And you probably are thinking, but we have the same number of protons, the same number of neutrons, the same number of electrons. How would the mass be different? Well, this comes back to relativity, where Einstein said that energy, this should have been writing, and mass are exchangeable. That is, mass is just a form of energy. And when you have the nucleus bound together, it's in a lower state energy. Otherwise, it wouldn't be bound together, right? If it was a higher energy, it'd break apart into lower energy. So because it's in a lower state energy, it has moved energy into mass. But if it breaks apart, or other way around, if it breaks apart, then you're going to move the energy out. And so mass can tell us about the stability of the nucleus. Now, the beta decay is the one that's more tricky. Notice this shows beta minus, because there's also beta plus. That's the next slide. So we have a parent nucleus here. So just following what we had here, we'll say it's the thorium-234. And it decays. We have the electron that came out of nowhere. Do not be confused and think that a neutron is equal to a proton plus an electron. That is not true. But what is happening is the neutron is actually being destroyed, and a proton and electron are being created along with this other thing. We call this an anti-neutrino. Anti means antimatter, and that bar over the top is what signifies that it's anti. This here is not a V, that's the Greek letter nu for neutrino. Neutrino, neutral, and tiny. So it's a tiny neutral particle. So we're going to have the beta with a -1 and a 0 plus protactinium 91. So the numbers on the bottom add up. 234, so the numbers on the top add up. Plus this electron antineutrino. It's neutral, so it has no charge. This is going to be a -1 charge. This is going to be a +1 charge. Initially, they just had this, like I wrote before. But then they noticed that energy momentum weren't quite conserved. And so, once again, you have a quandary. We've seen quandaries like this before. Were we wrong about the conservation of energy momentum, or is there something else? And so it was proposed that there must be a tiny particle with no charge, because they'd easily find it if it had charge. It had to be tiny because they'd easily find it if it was large, that was also involved. And so careful studying, they found this neutrino. At first they called it a neutrino, and then they realized for other reasons it had to be an antimatter particle. So it's an electron antineutrino. So that's the reaction for beta minus decay. But there's beta plus decay, as you can see from the slide down below. Well, what's beta plus decay? Beta plus decay looks like, but isn't, a proton decaying into, okay, the actual equations themselves are right without the equal sign, but it's correct if you put this. proton becomes. It's not equal to. A proton is not a neutron plus an anti-electron. A neutron is not a proton plus an electron. But that's the decay process. So a beta plus decay, and so I can't think of something offhand that undergoes beta plus decay, but you have, well, once again, let's just look up an example of something that does a beta plus decay and get it right. Just to give you a realistic example. So give me an example here. Okay, nope. Carbon 14 is a beta decay. Magnesium 11, or magnesium 23, excuse me, undergoes a beta plus decay. So because the beta plus decay has the net result of lowering the number of protons by 1, the beta plus itself carries a plus 1, 0, plus, and then I have 11 plus 1 will give me 12. And the 23, the superscript has to stay the same. So that's sodium 23. And of course, it's going to have a negative charge because it has one more proton but didn't add an electron. And then plus an electron neutrino. Notice this is not an antineutrino. The positron is an anti-electron. It's exactly the same as an electron, but it has a positive charge. And we call this an antiparticle. It's part of antimatter, which we will, again, talk about later. So beta comes in beta plus and beta minus. When we first indicated what the radioactive decays were, we only had beta minus there. But it turns out that there are both. Final thing for today, radiometric decay. Now we're going to do radiometric dating next lecture, but for right now, radioactive decay. Radioactive decay occurs when you have an unstable nucleus. Unstable means it's kind of like balancing your pencil on the eraser. You can balance it on the eraser, but if somebody bumps the table, it's going to fall over and fall to a lower energy state. Well, that's what it is to be radioactive. The nucleus is kind of stable, so you can put like an energy graph. You have something like this. So this here is unstable. It's locally stable, right? Just a little perturbation and it'll come back in. So this would be like, let's say R. Distance. You move it just a little bit, no big deal. But if you move it past here, then it falls down here. And it's got a big energy difference. And that energy is going to be released when it falls down to the lower energy state. Now, in studying these, what we've found, we scientists, not we as in me doing it, is that the decay of these unstable nuclei is controlled by statistics. There's a certain probability per unit time of decay. And so we call that the decay constant. So I have an element, and it depends on the shape of this energy graph I drew, what that decay constant is going to be. Some have big decay constants, which means that you are going to have a high probability of decay. Some have small decay constants where it's unlikely to decay. And so the number of decays per second, so A, we call the activity, number of decays per second, is equal to this probability of decay per unit time multiplied by n, which is the number of nuclei. Nuclei is just the plural of nucleus. And so this equation is a mathematically correct equation. The activity is the number of decays per second. If you have a decay, the number of nuclei is going to drop. A single decay drops by 1. So that's why we have these minus signs, because of the dropping. And so if you do this with calculus, the deltas become d's. There is a bit of a sign issue, I just noticed. I have a minus sign. I should only have one minus sign, not two minus signs. Should be dn dt is equal to minus lambda n. And so dn over n equals minus lambda dt. I know David can do this, and Maxwell, you're in calculus class, you should be able to do this. We've separated variables. You integrate both sides independently, and you have natural log of n final over n initial, because we do put limits. And so solving for n final, you have n final equals n0 e to the minus lambda t. So it's very straightforward calculus, and I know not most of you are not in the calculus class, so you don't have to be able to do that calculus. But it's a very straightforward calculus math that gives us an equation that says the number of radioactive nuclei remaining is equal to the number we started with, so n sub 0, and then e to the minus lambda t. Lambda is that decay constant, and t is time. And so if you graph this, you get an exponential decay. And it turns out that there is a certain time when n equals initial amount over 2, when you have 1/2. And that's going to be equal to, according to this equation, e to the minus lambda. I put t 1/2 here. And so we can solve that for the half-life, for the time when you have 1/2 remaining. So just reversing, coming back to this form of the equation here, natural log of n0 over 2 divided by n0 equals minus lambda t 1/2. So t 1/2, which we call the half-life, the time for half to remain, is equal to natural log of 1/2 over minus lambda. Now, if you're familiar with natural logs, you know natural log of 1/2 is minus natural log of 2. So this is equal to, notice there's a minus on bottom, natural log of 2 over lambda. Now, I will never forget when I was a college freshman taking general chemistry. I think I was a freshman. We had a test, and we had to do something that it wasn't half-lives, but it was something about concentrations, calculations. And we had a natural log of 2. And I put the natural log of 2 in my answer. I got marked off because I didn't put 0.693, because the teacher absolutely wasn't thinking. Natural log of 2 is 0.693, but it comes from the natural log of 2. So this is the definition of the half-life. And we usually, like I said before, we use a tau there. So the half-life is natural log of 2 divided by the decay constant, where the decay constant was the probability per unit time of a decay occurring. One of the things that's important is if I have 100, well, here it started with 1,000 nuclei. If I wait one half-life, I'll have 1/2 remaining. But if I wait a second half-life, it will cut that number in half. So this is 2 half-lives is 250. 3 half-lives is 125. The time to get to 0 is an infinite number of half-lives, although you asymptotically approach 0 as you get to a large number of half-lives. So next class period, we'll talk about how this plays into radiometric dating. So we'll talk carefully about this shroud of Turin next class period. Have yourself a great day.